If we want to interpret the estimates from OLS regression as measuring causal effects, then we have to be sure that the appropriate exogeneity assumption for OLS regression is satisfied. Often this is not a plausible assumption to make. For example, if there are omitted variables. This means if there are confounding variables that we can't include as controls, maybe because we are not able to obtain data on those variables. This can also be the case if there is measurement error, that is, if we don't observe a regressor, instead have to substitute it for an imprecise measurement or a proxy variable. Or this can be the case if there are equilibrium conditions that determine jointly a regressor and our outcome variable. If we cannot find a linear regression model that satisfies the exogeneity assumption for OLS regression, maybe because of any of these reasons, then there are alternative estimation strategies that we can use. And in this video, we're going to talk about one such strategy that is called instrumental variable regression. We'll introduce IV regression based on an economic example based on the paper on maternal labor supply by Josh Angrist and William Evans that we have talked about before. We are looking at mothers who have at least 2 children, and our variable of interest is a binary variable or a dummy variable, more kids, and it takes the value 0 for mothers who have exactly 2 children, and the value 1 for mothers who have more than 2 children. Our outcome variable is weeks worked, and this variable records how many weeks during a year a mother worked. The slope coefficient in an OLS regression with a single regressor is given by this expression. So to compute it, we have to compute a covariance and a variance. However, if the regressor is binary, that is, if it takes on only the values 0 and 1, then there's a simpler formula that requires us only to compute 2 means. Let's review this formula briefly, and in doing so, we'll just write for our regressor more kids x1 and for our outcome weeks worked y to simplify notation a little bit. Let's put our regressor x1 on the horizontal axis and our outcome y on the vertical axis. x1 takes on only the values 0 and 1. So in a scatter plot, all our data lies on one of these 2 gray lines. For example, our data may look like this. Let's compute the sample average of the outcome variable y only over the subsample where we see x1 equal 0, that is, over these observations. And let's suppose that it is here. And let's assume that the corresponding sample average for the x1 equal 1 subsample is here. Beta 1 hat is the slope coefficient of an OLS regression of y on x1. And we know that it can be written as the difference between this term and this term. Let me make slightly more sense of this expression by rewriting it slightly. So what I'm going to do is I'll take the right hand side and I divide it by 1 minus 0. So I'm dividing by 1. Dividing by 1 doesn't change anything. I can find a 1 in my graph by looking here. And I can compute this one by computing the average value of x1 on the subsample such that x1 is equal to 1. In this subsample, everyone has x1 equal to 1, so the average is also 1. Similarly, I can compute this 0 by computing the average value of x1 on the x1 equal 0 subsample. Let me use all this to rewrite my formula. I found a way to rewrite my formula for beta 1 hat as an outcome difference between two groups divided by an input difference between two groups. This principle is an intuitive recipe for computing an effect. For example, if you have two groups of people who follow different diets with different calorie intakes, an intuitive way of computing the effect on body weight of consuming an additional calorie is to take the difference in average body weights between the two groups and divide it by the difference in average calorie intakes. Or if you have two groups of mothers with different numbers of children, an intuitive way of estimating the effect of having an additional kid on the intensive labor margin is to take the difference in weeks worked between the two groups and divide it by the difference in the average number of children. For binary x1, this formula is slightly less intuitive because its intuition lies on a linear effect and the thought experiment of always adding one more, but with a binary regressor, once you are at 1, you cannot continue adding one more unit. Still, the general principle of the formula is very intuitive. We have divided our sample into a green group and an orange group. The group assignment was by value of the x1 variable. For example, we assigned all the observations for which we observed x1 equals 0 to the green group. Suppose that we have some other way of sorting observations into groups. For example, suppose that our data looks like this. For this data, we have found some alternative way of sorting observations into a green group and an orange group. For the green group, we have some observations for which we observe x1 equal to 0, and some for which we observe x1 equal to 1. And likewise for the orange group. We can compute the average outcome y for the green group and the average y for the orange group. For the green group, we sometimes observe x1 equals 0 and sometimes x1 equal 1. So the average value of x1 for the green group lies between 0 and 1, let's say here. And the average x1 for the orange group is here. Again, we have an output difference and an input difference. We can construct an effect estimator, beta 1 hat IV, and here I'm writing IV to make explicit that this is not the OLS estimator. And this will be equal to the output difference divided by the input difference. There are lots of different ways of sorting a sample into a green and an orange group. So what is a good way of sorting our observations into two groups? From our discussion of OV bias, we already know that the OLS sorting, so the sorting that sorts on our regressor more kids, is not a good sorting because it will also sort on a confounding variable. So a good sorting will be a sorting that sorts on our regressor, but not on a confounding variable. Our outcome weeks worked is determined by regressor x1 equal to more kids, and an error term u. And previously we argued that an important component of u may be grandparental childcare. There are two groups, a green group and an orange group. Each member of the population is assigned a value for more kids, for u, and is assigned to a group. For the members of the population who are assigned to the green group, what is the average level of more kids? Let's suppose it is this. The average value of more kids given that you are in the green group. And the corresponding average level for the orange group is here. These two population values can be estimated in a sample by the corresponding sample averages. So we can estimate where the two groups are in x1 space. The green group will be here, the orange group will be here, but we don't know where these two groups are in terms of u. On average, u is equal to 0. For the OLS sorting, we argued that the green group has bad childcare options and therefore a below average u value, so it could be sitting right sort of at this level, and the orange group has good childcare options and therefore an above average u. We argued that this implies that OLS doesn't estimate a ceteris paribus effect, instead it estimates the effect of simultaneously changing x1 and u. For the OLS sorting, we sorted on an endogenous variable, and by analogy we can call all sortings that sort on u endogenous sortings. An exogenous sorting would be one that doesn't sort on u. The average level of u in the green group is equal to 0, and the average level of u in the orange group is also equal to 0. If we compare the two groups from an exogenous sorting, then we're comparing two groups with different levels of x1, but similar levels of u. So all the outcome differences that we observe between the groups cannot be driven by differences in u. They have to be driven solely by the differences in x1. So the orange group can be considered a copy of the green group that differs only with respect to more kids. So in other words, by comparing the orange with the green group, we're moving horizontally, that is in ceteris paribus direction, and we are revealing the causal effect. Now it is time for us to move away from using colors to describe a sorting and introduce the concept of instrumental variables. Let's start by writing down our model equation. In the context of instrumental variables, this equation is often called the structural equation. By using the word structural equation rather than the word linear regression model, we emphasize that we really believe that beta 1 represents the causal effect of our variable of interest x1. We are willing to accept the risk that this interpretation of beta 1 forces us to write down a u that renders the variable of interest x1 endogenous, in the sense that the exogeneity assumption for all S regression is not satisfied. We assume that we can sample from a population that consists of the outcome, the variable of interest x1, and a third variable, z. Z is called an instrumental variable, or IV. Z is a dummy variable and takes the values z equals 0 and z equal 1. By sorting on our instrumental variable, we can divide our population into two groups. Based on these two groups, we can compute our sorting estimator. This estimator is called the IV estimator. Our hope is that the IV estimator estimates our parameter of interest beta 1. For the IV estimator to work as desired, two assumptions have to be satisfied. The first assumption says that the conditional expectation of the error term given the instrument is 0. This assumption says that the instrument cannot be used to predict u. Or in other words, by observing z, we do not obtain any information about the level of u. This assumption is called the instrument exogeneity assumption. This assumption ensures that when moving from one group to the other group, we can never move vertically, so that the only possible direction of movement is horizontally in the direction of the causal effect. Our second assumption says that the expected level of x1 in the subpopulation with z equal 1 is different from the expected level of x1 in the subpopulation with z equal 0. This assumption ensures that different z values have different typical values of x1. This assumption is called instrument relevance. The instrument relevance assumption ensures that when moving from one group to the other, we are moving in the horizontal direction. If instrument relevance is not satisfied, then both groups have the same typical level of x1, and the causal effect of x1 cannot drive an outcome difference between the two groups. Our identification idea does not work if both groups have similar outcome levels. We can of course only use variables that are observed as instrumental variables. Often it's not easy to find an instrumental variable that is observed and that satisfies these two assumptions. For our economic application, it turns out there is a very clever way of defining such an instrument. Recall that our population of interest were mothers with at least 2 children. So for example, a mother could have exactly 2 children, or maybe 3 children, like the family I drew here. Now I'm assuming that all the children here are depicted in birth order, so that the oldest child is on the left hand side and the youngest child is on the right hand side. Our variable of interest is more kids, and more kids takes the value 1 if the mother has more than 2 children, like the family I depicted here. And more kids is equal to 0 if the mother has exactly 2 children, so that the family would look like this. Our instrumental variable will be a variable called same sex, and it takes the value 1 if the first 2 children have the same sex. That is, if the first 2 children are either 2 boys or 2 girls. If the first 2 kids are of different genders, then the same sex variable takes the value 0. This covers the cases first a boy and then a girl, or first a girl and then a boy. To determine the value of more kids, we don't have to know the sex of the first 2 kids. But to determine the value of same sex, we do. For example, we have same sex equal to 0 if the first child is a boy followed by a girl. So we would simultaneously have same sex equal 0 and more kids equal 0 if the first child is a boy and the next child is a girl, and if then no additional child follows. To have same sex equal 0 and more kids equal 1, for example, we can have first a boy, then a girl, and then a third child, and the sex of this third child does not matter. We have same sex equal to 1 for example if the first 2 children are boys. We want to use same sex as an instrument. Let's check our IV assumptions. We'll start with checking instrument exogeneity. We previously argued that the variation in more kids is informative about the level of U. In particular, we said that the families down here may have strategically decided to have this third child because they have much better childcare options than the families up here. So the families with more kids equal to 1 were more likely to be up here rather than down here compared to the families with only 2 children. Can we make a similar argument when looking at the variation here? No, we cannot, because the sex composition is essentially random. So observing boy-girl rather than boy-boy shouldn't be predictive of the level of childcare that I have available. The exogeneity assumption seems plausible. Next, let's check the instrument relevance assumption. The instrument relevance assumption requires that the typical level of more kids is different in the same sex equal 0 and same sex equal 1 columns. We may obtain different levels of more kids in the 2 columns because of a preference for gender balance. A lot of couples want to have both a boy child and a girl child. So if the first 2 children are a boy and a girl, the couple may be happy to have no more children. They become part of the more kids equal 0 population. If, on the other hand, their first 2 children are 2 boys, then they may decide to have yet another child in the hope that it will be a girl, and they will become a part of the more kids equal 1 population. If this reasoning is correct, then we expect that in the same-sex equals 0 group, the average level of more kids is low, so that the typical same-sex equals 0 group would be maybe here. And we would expect the average level of more kids to be higher in the same-sex equal 1 group, so that the expected same-sex equal 1 observation would be here. The instrument relevance assumption seems also plausible. In this video, I introduced instrumental variable regression. Instrumental variable regression is motivated by the fact that a regressor is endogenous if it's sorting on the error term, and in that case, OLS does not estimate the ceteris paribus effect that we're interested in. If we observe an instrumental variable that satisfies both the instrument extraneity assumption and the instrument relevance assumption, then we can sort observations into 2 groups. And if we compare these 2 groups, we reveal the ceteris paribus effect.